In this segment, we're going to talk about another way in which System 1 pushes you around, even when you're thinking using System 2. And this is a particular fallacy called the conjunction fallacy. This one is relevant not just to assigning particular numbers like the age of Gandhi or the height of a redwood, but instead to assigning probabilities, to deciding what's more probable than what. So this example we went over last time, so I'm just going to go through it very quickly. You're given this description of Linda. It includes that she's a social justice activist and active in anti-nuclear demonstrations, or at least she was when she was in college. And then you're asked to rank a series of options. For our purposes, only two of these options matter. The option that Linda is a bank teller and is active in the feminist movement, that is, that she meets both of those conditions, and the option that she only meets one of those conditions, that Linda is just a bank teller. And maybe also active in the feminist movement, maybe not. Here's the results. If you look at undergrads in the very first time this experiment was done, you got about 90% chose Linda is a bank teller and active in the feminist movement as more probable than Linda is a bank teller. In our class, it was about 5 and 6. If you look at graduate students in the decision science program at Stanford, you get about 85% saying it's more probable that she's both a bank teller and a feminist than that she's a bank teller. Other groups like statisticians, that number will drop down quite a bit. So if you give only these two options, you still get about 85% choosing one over the other, choosing a bank teller and feminist over bank teller. And that's because the reason that matters is you might have thought, well, it's just there's so many options that I'm a little confused and I lose track of what's going on. But even when given just two options, most people, in fact, about the same number of people, still pick feminist and bank teller as more probable than just bank teller. Again, just to reiterate, we went over this in class and in the last video, but just to reiterate, that's objectively incorrect. So if I ask you, is it more probable that you're either in Des Moines or somewhere else in the US on the one hand, or that you're in Des Moines in particular, somewhere else in the US in particular, you'd have to say it's more probable that you're in either of those places than that you're in a particular one, because the either option includes both options. Here we'll look at this question. Is it more probable that you're in the USA somewhere or other, including in the lower 48, or that you're in the lower 48 in particular? Well, it has to be more probable that you're somewhere or other in the United States because that includes the lower 48, but the lower 48 doesn't include all options of being in the United States. And this problem has the same structure when we say, is it more probable that you're both a feminist and a bank teller than it is that you're a bank teller? The answer has to be that it's more probable that you're a bank teller because that includes the option of being a feminist bank teller, whereas being a feminist bank teller doesn't include all ways to be a bank teller. Again, we went over that last time, so I'm going to assume you've now understood that point and move along. We know that A and B can't be more probable than A because B adds an extra condition that you have to satisfy A and B. But we ignore this when assigning probabilities in this case. Why? Because System 1 pushes us around. System 1 loves descriptive information. It loves information about similarity. It gets driven by that kind of information. And that descriptive information, that information about similarity, plays a role in assigning probabilities, leading you to think that feminist and bank teller is more probable than bank teller. How do you protect yourself against this love that System 1 has for descriptive information, for similarities? Engage System 2 is the first step. But then what do you do when you engage System 2? Well, one thing you can do is use any merely statistical information you have. For example, if you know, as you do now, that the conjunction A and B can't be more probable than either A or B taken individually, then if you see options where one of them is the conjunction A and B and the other one is either A or B taken individually, you just always assign a higher probability to the one taken individually than the conjunction of both. Sorry, those things appeared out of order. Okay. And another thing you can do is to question how well any descriptive information you have predicts what you want to know. So in this case, although being a social justice activist predicts being a feminist, it's not a perfect predictor. It's possible to be a social justice activist and not be a feminist at all. Similarly, it's possible to be an anti-nuclear activist and not be a feminist at all. So although each is a predictor of being a feminist, they're not perfect predictors, so they don't provide a guarantee. When you don't have a guarantee, you have to look not just at that descriptive information, but other kinds of information you have, including background information about how probabilities work. Okay. This is an instance of a more general point. And the more general point is that we should look for mere statistical explanations for facts that we encounter, but we tend not to do this at all. That is, we tend not to look for mere statistical explanations. So in order to understand this, you need to know what a mere statistical explanation is and what a causal explanation is. So let's look at another example from the handout. There was a question that asked you about kidney cancer in rural communities and incidence of kidney cancer. And some people had the following. It said, a study of over 3,000 counties finds that the 3 counties with the lowest incidence of kidney cancer are rural and sparsely populated. And some people had a study of over 3,000 counties finds that the 3 counties with the highest incidence of kidney cancer are rural and mostly sparsely populated. In fact, both of these things are true. So I wasn't lying to you in either case. So you were then, told this, and then the question is, well, why is it the case? And when I ask you why, about nearly all of you, not quite all of you, but nearly all of you, about 45 out of 60, gave what are called causal explanations. So, for example, you might say the reason, if you were given the lowest as the thing, you might say, well, the reason that these rural, sparsely populated areas have the lowest incidence of kidney cancer is because their water is cleaner and there's less pollution than you get in the dirty cities. But if you were given highest, then you might say, well, the reason these rural counties have the highest incidence of kidney cancer is because their water is more polluted because of all the runoff from farms or whatever that doesn't get cleaned by high-powered, expensive filtration plants. So in one case, you might point to the water containing more carcinogens. In one case, you might point to it having less carcinogens. Well, it's not like people who were given the lowest incidence of kidney cancer version of the question were antecedently inclined to think that rural areas have particularly clean water, and people who were given the highest incidence of kidney cancer version of the question were antecedently inclined to think that rural areas have especially dirty water. Instead, what happens is you're given a fact, and you look for a causal explanation. You think, okay, if people in rural areas have the lowest incidence, there must be something that causes that. It must be the cleaner water or the cleaner air. And if you're given the highest incidence, you look for something that causes that. It must be the dirtier water or the dirtier air or whatever. People sometimes also point to diet in each direction. They'll say that if you're given the lowest, you'll say, well, people in rural areas have better diet because they have access to that good farm food. And if you're given highest, people will say, well, you don't have access to as diverse a range of foods, so you eat worse, and that's what causes the cancer. Okay, well, what's the and I should say most subjects offer causal explanations for any fact they're given, not just this fact. As I said, in here, about 45 out of 60 gave causal explanations. Incidentally, 12 of the 15 who didn't give causal explanations, who gave the right kind of explanation, were in the low incidence group. So that suggests that those people would have sought a causal explanation, except it didn't fit with their expectations about which group would have a lower incidence. So why is it? What's going on here? This I already mentioned, that people told that small counties have the lowest incidence tend to say they eat better, drink cleaner, and are less stressed or whatever, and people given the highest incidence for rural counties say they eat worse, drink dirtier water, and are more stressed, looking for facts that fit with the answer they picked. But what really drives the answer? That is, what really drives the fact that both the lowest and highest incidences occur in small counties? Well, very few people consider what really drives it. In order to see what really drives it, let's consider another example. Here we have 2 people. I've labeled them A and B. A has a 4 on her shirt and B has a 7 on his shirt. Each is going to draw balls from an urn. Let's suppose we can see into the urn, but they can't. So the urn is actually dark from their point of view from the outside, so they don't know what color balls they're grabbing. They're just grabbing at random. Now, A is labeled 4 because A is going to grab 4 balls, and B is labeled 7 because B is going to grab 7 balls. And here's a really simple question. Which of the 2 is going to get a homogeneous sample, that is a sample with all the same color balls, more often? Well, if you reflect on it for a second, hopefully you'll pick A. Since A is only drawing 4 balls, it's more probable that A gets 4 of the same color. A, of course, isn't going to get 4 of the same color every time. In fact, most times A won't get 4 of the same color, but it'll happen upon occasion. And it will happen upon occasion for B too, even though B draws 7 balls, just less frequently. So we're assuming this urn has half red and half blue balls. A plucks 4 balls and B plucks 7. which gets a homogeneous sample more often? Well, if you do the math, A will get a homogeneous sample, assuming that A is drawing randomly about 13% of the time, and B will get a homogeneous sample about 2% of the time. So A is going to get a homogeneous sample far more often than B, because A is drawing out smaller samples than B is. The point here, the general lesson that this EARN example reveals, is that extreme outcomes, where you have homogeneous samples, samples that are uniform, are more likely to be found in small samples. The smaller the sample you're taking, the more likely it is that you get all blue or all red. Now let's think about the kidney cancer case in light of this. Small counties are like small samples of balls. They have comparatively few people in them. Large counties are like large samples of balls. They have comparatively more people in them. And that's why small counties tend to be the most extreme when it comes to both the lowest and highest incidence of kidney cancer. Because if you have a county, think about it in the extreme case. If you have a county that only has one person in it, and that person happens to have kidney cancer, then that county has 100% of the people with kidney cancer. And if that person happens not to have kidney cancer, then that county has 0 people with kidney cancer. Now, you can imagine raising the size of the county to 100. If just by chance 10 of the people in the county have kidney cancer, then it's a 10% rate. And if just by chance nobody does, then it's a 0% rate. Well, if you have a county with 1 million people in it, it's far less likely that just by chance you're going to have 100,000 of them with kidney cancer or 0 of them with kidney cancer. So the bigger the sample you're pulling from, the more likely you are to get a representative sample, and correspondingly, the less likely you are to get an extreme sample. And this is called a mere statistical explanation. It's the way you sample that produces the result, that produces the fact that the small counties have the lowest incidence of kidney cancer, and also produces the fact that they have the highest incidence of kidney cancer. It's the way you're sampling, it's not the world. So there isn't really a cause for why they have the lowest and why they have the highest. Instead, it's just a statistical artifact. It's a fact about how you're sampling. Okay. It's important to understand this. So why is it important to understand this? Well, let's consider another example. Research repeatedly finds that the most successful public schools are very small, with very few students. Okay? Well, it turns out that research also repeatedly finds that the least successful public schools are very small, with very few students. And we now can see why that is. The answer is the same in both cases. Small schools have fewer students, so they're smaller samples. If you have a school with just 6 kids in it, it's much more likely that they'll have extremely low SAT scores or extremely high SAT scores than it is if you have a school with 5,000 students in it. Because in the school with 6 students, just 3 abnormal students will skew things heavily in favor of either very high or very low scores. Where if you have a school of 5,000 students, it would take a whole lot of unusual students to be there to skew the scores in either direction, especially large way. Okay, so again, you're more likely to find extreme outcomes in small samples. And I said this matters. It matters because there was a study published that found that the most successful public schools were on average very small. And this study got a lot of press. And after it got a lot of press, the Bill and Melinda Gates Foundation, one of the biggest charitable foundations in the world, invested almost $2 billion in small schools, giving small schools money and breaking up large schools to make them smaller. They had various partners in the government, various other private charitable foundations, all sorts of money raised to break small schools and break up big schools and make them smaller because of this fact that was discovered that small schools have the best outcomes. That is, the best outcomes tend to occur at small schools. But that presumes that the reason you get the best outcomes at small schools is because of some causal reason, some fact about the nature of the schools that makes the students better. But in fact, that's not true at all. When it was looked at more carefully after this money was spent, while the money was being spent, it turned out that it was just a sampling artifact. It's just the fact that it was a small samples. Small schools are small samples that causes, that is why they have the best outcomes. They also have the worst outcomes. Why? Because they're small samples, so you get extreme outcomes, more homogeneous outcomes more often. Okay, so this is crucial in part because we are cause-seeking machines. Anytime someone gives us a fact, we try to identify the cause. We have almost no sort of innate temptation, automatic temptation to look for mere statistical explanations, even when those are far more likely than causal explanations. And that, again, is because we're cause-seeking machines. It's what we do. So how to protect yourself? Well, again, this fallacy operates via system 1, so you need to invoke system 2. And when you invoke system 2, what do? Before explaining anything that someone wants you to explain, before saying, here's why it's that way, always look for a mere statistical explanation. You're not going to have any problem looking for causal explanations. That's what we're tempted to do. So you have to sort of push yourself in the other direction. Consider, is this a measurement artifact? Is it an artifact of the way I sampled? Is it merely a statistical phenomenon and not something that requires a causal explanation? Okay? And as I say here, more generally, just always consider how the portion of the world you've sampled might not represent the world as a whole, might be misleading. Something we're not tempted to do, but we really need to do if we want to think accurately about the world. Okay, we'll stop there and consider the coin flipping next time.